In our last lecture, we talked about the Heisenberg uncertainty principle and how because of this principle, we can't know exactly where an electron is going to be. But what we can know is we can come up with a prediction for where the electron is most likely to show up in an atom. So this is a probability distribution diagram, or a probability distribution map, and in chemistry, we call this an orbital. So an orbital is the area of an atom where an electron is most likely to show up. And in order to identify an orbital and the electrons that inhabit it, we use what are called quantum numbers. So orbitals are identified by their quantum numbers. And there are 4 different quantum numbers that we're going to talk about. The first quantum number is the principal quantum number. I'm just abbreviating quantum numbers as Qn. And the principal quantum number is designated as a lowercase n. And this quantum number determines the size and energy of an orbital. It has several possible values. Its possible values are positive integers. So that would be n equals 1, n equals 2, 3, 4, and so on. And we can find the energy of, we can use n to find the energy of an orbital using the equation E equals negative 2.18 times 10 to the negative 18th joules times 1 over n squared. And that number here, this value, is another version of the Rydberg constant. Notice the difference between this version of the constant and the one that we used in the wavelength form of the Rydberg equation from our previous lecture. So the difference is these units. So it's always important to make sure that your units are lined up with the correct value, and I know we've talked about that a lot so far this semester. So that is our principal quantum number. The second quantum number is called the angular momentum quantum number. And it's designated by a lowercase l. And I'm doing that as a cursive L just to make it clear that it is not the number 1. And the angular momentum quantum number determines the shape of an orbital. And the possible values of L could range from 0 all the way up to n minus 1. So that means that if n equals 1, then L equals 0. If n equals 2, then L could equal 0 or 1. Oops. And if n equals 3, then L could equal 0, 1, or 2. So L could be 0, and it could be any number up to n minus 1. And these values of L are assigned letters to describe the shape of an orbital. So if we have our value of L, that value is associated with a letter that describes the orbital shape. So a value of L equals 0 represents an s orbital. The value of L equals 1 represents a p orbital. L equals 2 represents a d orbital. 3 represents an f orbital. And there are other shapes of orbitals. We're just not going to go any further than f orbitals in this class. So make sure that you go to your textbook, and it has really great diagrams of all of those shapes, and you're going to want to be able to recognize s, p, and d orbitals for this class. I'm not going to test you on f orbitals. If it's not one of the s, p, or d orbitals and it shows up in a homework assignment, assume it is an f orbital, because again, we're not going any further than that, and I don't need you to be able to recognize f's. I just need you to be able to recognize s's, p's, and d's. Our third quantum number is the magnetic quantum number. And that is designated by m with a subscript lowercase l. And this determines orientation of the orbital. And what that means is it determines the direction the orbital is facing. And the possible values of m sub l can range from negative L to positive L. So what that means is if L is equal to 0, then m sub L can only equal 0. If L equals 1, then m sub L could equal negative 1, 0, or positive 1. And if L equals 2, then m sub L could equal to negative 2, negative 1, 0, positive 1, or positive 2. And again, these determine the direction that the orbital is facing. And our last quantum number is the spin quantum number. And the spin quantum number doesn't actually refer to the orbital itself. It identifies individual electrons that are within that orbital. And that value is called m sub s. So we have m sub l and m sub s. And what this does is it identifies the direction of the spin of the electron. And there are two options here, because we know that an orbital can hold 2 electrons at a time, so there are 2 options for the possible spins: spin up or spin down. And the numbers that are used to identify these spins are positive 1/2 or negative 1/2. So a spin quantum number cannot be any number other than positive or negative 1/2. It can't be a whole number, can't be an integer. It has to be positive 1/2 or negative 1/2. So using those rules, let's take a look at an example of how these numbers actually work together. So I'm going to give you a set of quantum numbers, and these quantum numbers are supposed to specify an orbital, so they're going to be the first 3 quantum numbers. But in one of these numbers in the set is going to be a number that's not allowed. So we're going to replace the quantum number that's not allowed with one that is allowed based off of the rules. So for A, here's our first example. If n equals 4, L equals 1, M sub L equals negative 2. So what can we do to change this set of numbers so that all of these numbers are allowed? So I'll give you a second. You can pause the video and solve it on your own. Well, there are 2 options here. Option 1 is that we change L to equal 2 or 3, because what that will do is it will allow this M sub L value to be within the confines of that L. Alternatively, we could change M sub L to negative 1, 0, or positive 1. And making either of those changes would correct this set of quantum numbers. So for B, let's say we had n equals 3, L equals 3, and M sub L equals positive 2. Which number here is not allowed? In this case, it's the L value. So in order to make this set of quantum numbers allowed, and by allowed I mean it follows the rules that I just laid out, then we can change the L value to 2, because that obeys the rule that L cannot be greater than n minus 1. And it still fits the rule with our M sub L values, where M sub L could be from negative L to positive L. Let's do one more. Let's say we have n equals 1, L equals 1, M sub L equals 0. So this example is similar to the previous one. We could change our L value to equal 0. And now that I'm looking at these, I suppose that there is another change that could be made. You could also change the n values here. You could change n to equal 4 so that it's at least 1 greater than L. And here, you could change n to equal 2, and that would leave the L and the M sub L as numbers that are allowed. So either of those changes would allow these numbers to follow all of the rules.